In this presentation, I'm going to do a basic switching review of just a preliminary overview of some of the stuff you should already have learned in the CCNA, but just to give you a refresher before we moved on to some of the more advanced switch topics that you would expect to see in the CCNP switch exam. So let's start right from the very beginning. You should know going into the exam everything that's in this module here, definitely. This is stuff that you already learned at the CCNA level. For example, switching is based on destination MAC addresses. Now remember, at the CCNA, you learned that switches were layer 2 switches. Basically, a switch would take an incoming Ethernet frame, look at the destination MAC address, and based pretty much purely on that, decide where this frame was supposed to go. Now, as we're going to see here coming up in some other successive videos where I talk about the concept of multi-layer switching, we're going to see that in reality, many switches these days, most switches that Cisco sells, are actually capable of not only looking at the layer 2 MAC addresses, but even deeper into the packet at like IP addresses and TCP UDP port numbers. But at a bare minimum, you need to know that MAC addresses are critical to switching. Now, upon parsing the MAC address, the switch could do one of 3 possible things with that frame. It could decide to forward that frame out one particular port. It could flood that frame. Flooding typically means it copies it and sends it out 2 or more ports. Usually we think of flooding as meaning it's going to copy it and send it out all the ports in the VLAN. Or it could discard that frame. It might say, I don't need to deal with this frame, or I don't have enough information to forward this frame, but that's what we mean by discard. Now, there's a lot of stuff about the MAC address table, sometimes called the CAM table, that we learned at the CCNA level that you also need to be familiar with for the CCNP. For example, how are MAC addresses put into the table in the first place? You should be familiar with that. So we know that MAC addresses in the table come in one of basically 2 flavors. There are static MAC addresses and dynamic MAC addresses. Static MAC addresses are those MAC addresses that the moment you power on your switch and turn it on, the switch's CPU already has some reserved MAC addresses that it knows about for certain reserved protocols, and it automatically populates the MAC address table with those MAC addresses. MAC addresses that correspond to things like the Cisco Discovery Protocol or the Dynamic Trunking Protocol and many, many others. So those are static MAC addresses. You can't really modify those. There's no timers associated with them. They're just automatically populated. Dynamic MAC addresses simply means that as an Ethernet frame comes into the switch looks at the source MAC address of that frame. It goes into the MAC address table and it says, do I already know about this? Do I already have this in here? If the answer is no, then the switch takes that source MAC address, puts it in the MAC address table, and also associates it with the inbound port where we received it and the VLAN where it was learned on, what that port was configured for, and then it associates a timer with that address as well. And we call that the aging time or the inactivity timer. Now, you should also be familiar with the answer to the question, how long is that timer? If we never see a frame from that particular source again, how long will it remain in the MAC address table before it's aged out? And the answer to that is 300 seconds or 5 minutes by default. So you should be familiar with all of that. And similarly, if a port on the switch physically goes down, well then whatever MAC addresses were associated with that port are automatically removed from the MAC address table. We don't have to age them out. So here are a variety of iOS commands you'll want to have memorized with regards to viewing and manipulating the MAC address table. You can just see here from the top down, the first command is for modifying that aging timer if you want to make it more or less than 300 seconds. You could also put static MAC addresses into the table. If, for example, you have some device connected to your switch that only receives traffic, it never sends anything. Well, if that device never transmits a frame, the switch will never learn its MAC address and be able to associate its MAC address to the port where it's connected, which means any traffic going to that device will have to be flooded because the switch won't know where it lives. So adding a static MAC address could solve that problem. And here's also some show commands here where you can see quantities of MAC addresses, the specifics of them, and so on and so forth. Okay, VLANs and trunks. You should be able to answer this question. What problem is solved by VLANs? Why do people use them? Why do we create them in the first place? Basically, we want to have groups of users separated into different broadcast domains. And we want to prevent the flooding of traffic from one group of devices into another group of devices. Or we want to implement some security policies. And it's just easier to do that if devices are in different broadcast domains. We also should be aware by this point that you can extend VLANs between switches by using VLAN trunks. And you should know sort of the differences between ISL and 802.1q. The ISL is Cisco proprietary, 802.1q is an IEEE standard. You should know what this thing called the native VLAN is and how it relates to ISL and 802.1q. That ISL doesn't really have the concept of a native VLAN, that every single Ethernet frame that goes across an ISL trunk gets encapsulated inside of an ISL header. Whereas with 802.1q, if a frame belongs to the native VLAN, we don't touch it. We don't modify it in any way. But all other frames that belong to non-native VLANs get a special tag applied to them. And we'll see what that tag looks like here in just a moment coming up. Also with 802.1q, the native VLAN is changeable. But if you do decide to change it from VLAN 1, which is the default native VLAN, to something else, got to make sure you change it on both sides of the cable to be identical. You should also be familiar with this acronym DTP. What is it? What's it used for? How do you configure it? So DTP stands for the Dynamic Trunking Protocol. So if you want to bring up trunking negotiation between two switches and have them bring up the trunk dynamically and maintain the trunk dynamically, DTP is a Cisco proprietary way of doing that. It's a Cisco proprietary protocol. And DTP has various different modes. For example, when you do the switch port mode trunk command, that means that you're forcing the interface to be trunking. It doesn't care what it's connected to. It will be forced to be a trunk. But DTP will still go out as a courtesy. So if the other side of that cable is something that's dynamic, it can use that DTP to form a trunk. But switch port mode trunk, there's no negotiation on that side. You're forcing it. Now on the dynamic side, you could do switch port mode dynamic desirable or switch port mode dynamic auto. And you should know what the differences are between those two. Auto means you are passive. You're passively listening for incoming DTP. And if you hear some, you can go ahead and reply back to it and become a trunk. Desirable means you are the initiator. You are the originator of DTP. You are preemptively trying to take some action to bring that trunk up. And then lastly, if you're trunking to something that doesn't support DTP, like a Cisco router or a non-Cisco device, maybe you don't even want to do switch port mode trunk, because switch port mode trunk would mean you're sending DTP as a courtesy, and we don't know how that device is going to respond to DTP. So in that particular case, you can't do any kind of negotiation. You'd have to force it. So you could do switch port mode trunk, but then the second command you'd want to do is switch port no negotiate. Switch port no negotiate goes hand in hand with switch port mode trunk. It basically says don't send DTP at all. Be quiet. So here's just an example of that 802.1q tag. You should know where it is. That's placed immediately after the source address. You should know how big it is. It's 4 bytes. So it's the same size as an IP address. So that might help you to remember that, an IP version 4 address. You can see the various different fields right here. So the tag begins with a tag protocol identifier, which is basically like an Ethernet type code. And you don't see it here in the sniffer trace, but the tag protocol identifier is always the same number. It's typically 0x8100 in hexadecimal, 0x8100. So when an incoming device sees an Ethernet frame with a type code of 0x8100, it says, oh, this is a .1q frame, and there's a tag right behind this. Then we've got 3 bits of priority, which you can use for quality of service, and we'll talk more about that when we get to the quality of service video. You've got a canonical and format identifier. You see, 802.1q is pretty old. Actually, when it was first invented, it was designed to operate on either Ethernet frames or token ring frames. Don't have to worry about token ring anymore because hardly anybody uses it, but the canonical and format identifier, depending on whether it was a 0 or 1, would indicate whether this .1Q tag is carrying an Ethernet or a token ring frame. Don't have to know any more than that. And then the last 12 bits encode your VLAN. So in this particular sniffer trace, we can see here that VLAN being encoded as VLAN number 2. So managing VLAN trunks, now when you configure a VLAN trunk and when a VLAN trunk comes up between switches, by default, all the broadcast domains that are active on that switch, in other words, all the VLANs that are active on that switch, are allowed across that trunk. But there are ways that you can control that, you can manipulate that. You should be familiar with this command, switch port trunk allowed. And you can see there's various permutations here. For example, the switch port trunk allowed VLAN remove command does exactly what it says. It says, I do not want these particular VLANs allowed on this trunk. In this case, I'm removing VLANs 3 and 4. And so you can see in the VLANs allowed on trunk section, 3 and 4 has been removed. You can also take VLANs that were previously removed and add them back in with the add command. You could say except, you could say switch port trunk allowed VLAN except 3, which means all VLANs except VLAN 3 are allowed on here. So this is a useful command. Definitely should know how to play around with this. And when it comes to configuring VLANs, so the normal range VLANs are from 1, so here's the entire range of VLANs, 1 through 4094. That gives you your entire range of VLANs. So the biggest VLAN you could ever manually create is VLAN 4094, and that's it. So as we can see here, VLANs 1 through 1001 are what's considered normal range VLANs. And these are VLANs that can be carried by VTP. They can be propagated between switches. Nothing special you need to do to configure and use these VLANs. Then we got some VLANs in the middle, 1002 through 1005, which are really old. Those were reserved for token ring. Can't really touch those, nothing you can do with those. And then VLANs 1006 through 4094 are considered extended range VLANs. Now if you want to use those numbers or any numbers in that range, there are some gotchas and some caveats you need to be aware of. So for example, you lose the benefits of VTP, the VLAN trunking protocol, if you want to do this. You have to have your switch in VTP transparent mode, unless you can use VTP version 3. But most switches don't support VTP version 3. It's very difficult to build an entire network topology of switches where they all support VTP version 3, unless you're buying like all the same model of Cat 4500 or something like that. So because VTP version 3 is difficult to get using in your entire topology, typically we just say you lose your benefits of VTP if you want to use extended range VLANs. Now also notice that when you create these VLANs, they are not stored in your normal VLAN.dat file. Why do we care? Well, because that means if you convert back, you say, well, I really want to go back to using VTP. I want my switch to be a server or a client. I like the benefits of it. Well then, now you have to do all this extra manual work. You can see here you got to delete those extended range VLANs. You got to delete them manually. And if you had any switch ports that were currently using those, now you got to go to those switch ports and move them over to a normal range VLAN. So there's two ways of configuring VLANs. There is the legacy method called the VLAN database method, where as you can see you just typed in VLAN database and then you typed in your VLAN ID. And then there's the more modern method, which is going into global configuration mode and typing VLAN and the number. Now what's the difference between these two? Well, strongly recommended that you not use VLAN database mode. Most people these days don't. Typically the only people you would see using VLAN database mode is somebody who, you know, has been working on Cisco switches for at least 10 years and this is the way they learned it, 10 years ago, and they just continued using it ever since then. But there's some big downsides to this. There's a lot of other features that won't work if your VLANs were configured using VLAN database mode. You'll lose access to several other features, so just a better idea to configure VLANs at global configuration mode and not limit yourself in that way. Now notice here, in this example, I'm trying to create an extended range VLAN. I'll expand this for you a little bit. Trying to create VLAN 2000, and it's actually telling me, it's saying, sorry, can't do it. You're not currently in the right VTP mode to do that. So, but when I change it over to VTP transparent mode, then no problem. It lets me create that VLAN without any issues. Now you should probably know for the exam, just from memory, that you need to be in VTP transparent mode to create extended range VLANs. But you can see here in practical reality, if you're not, it will warn you and it just won't work. Let's talk a little bit now. Let's just finish up with the topic of ether channels. So what problem is solved with ether channels? Well, the problem is we want to give ourselves more bandwidth between the same pair of switches without spanning tree blocking us by doing loop detection. You see, normally if I have 2 or 3 or 4 connections between the same 2 switches, spanning tree will see that as a potential loop, and it'll block pretty much all of your cables except for one. You'll be left with one cable that's forwarding on both sides, but everything else will be blocked somewhere, which means it's basically not usable. So by doing ether channeling, we're taking those physical cables and bundling them into one port channel. A port channel, as seen by spanning tree, is just one big logical point-to-point connection between 2 switches, and it doesn't block either side because it views it as like a single cable. So if you want to configure an ether channel, just like with trunking, you've got some choices. You could manually force it, or you could use some dynamic protocols like you see here of the port aggregation protocol or the link aggregation control protocol. Let's talk a little bit about those. So PAGP, you learn about that at the CCNA level. That's Cisco's proprietary protocol for dynamic bundling of ports into an ether channel group, otherwise known as a channel group. LACP, as you can see, is the IEEE standard. And you can see here it was initially defined in 802.3 AD. Probably should memorize that. And then later redrafted as 802.1 AX. Now, what are some other differences here? Well, you should know that PAGP and LACP have different modes of operation. So when we were talking about the dynamic trunking protocol, DTP, we said you could do switchport mode dynamic desirable, dynamic auto, switchport mode trunk. Those were considered trunking modes. Well, there are ether channel modes as well. And the keywords you select would be different based on if it's LACP versus PAGP. Let's talk a little bit about that. So with PAGP, the port aggregation protocol, actually with both of them, LACP and PAGP, one thing they have in common is using the channel-group mode on command. So if you say channel-group and then you give it some number, like 1 or 2 or 3, and then you say mode on, whether it's PAGP or LACP, the net effect is the same. You're forcing it into an ether channel. You're not doing any kind of dynamic negotiation whatsoever. And you're not sending anything out. That's a little bit different than with trunking. With trunking, when we did switchport mode trunk to force it to trunk, it was still sending DTP as sort of like a courtesy for the other side. But with ether channeling, when you say channel-group mode on, there's nothing leaving that port. There's no PAGP, no LACP, and it's just forcing it to be an ether channel. So it has no way of detecting what's on the other side at all. Now, if you want to do some sort of dynamic ether channeling, well, then you've got some choices. If you do port aggregation protocol, just like trunking had auto and desirable, PAGP has auto and desirable as well. And it works exactly the same way I just described with trunking. So not really going to get into that. With LACP, we have something equivalent. Instead of auto, we call it passive. And instead of desirable, we call it active. So LACP has passive and active modes. Now there's a few other things here, differences between the two that I should point out, little operational characteristics. For example, if you want to bundle several ports together between switches, but those ports are operating as half duplex, maybe because there's a hub in the middle, or I don't know, but for whatever reason they're half duplex, you can only use PAGP. LACP does not work on half duplex ports. LACP will only work on full duplex ports. The port aggregation protocol can be either half duplex or full duplex. So you got a little bit more flexibility there with the port aggregation protocol. But on the other side of the coin, with PAGP, currently you can have a maximum of 8 ports bundled into an ether channel, and that's it, which is still quite a lot. But if you start losing your ports, like let's say somebody accidentally pulls out a cable, now you just lost some of your bandwidth. Your total aggregated ether channel bandwidth has just been reduced. With LACP, you still have a maximum of 8 active ports that can be bundled into an ether channel, but you can have other ports above and beyond that that are in standby mode. So that if one of your LACP active ports gets yanked out or something, one of your standby ports can immediately join the group and take its place. So there is no loss of bandwidth. So that's a big benefit of LACP. Now, another difference with LACP is that it has this concept of system priorities and port priorities. Now, think about this. This will hopefully be a good analogy to help you memorize this. Remember, LACP, who's the organization that standardized it? The IEEE, right? IEEE also standardized spanning tree. Spanning tree also has priorities, system priorities, now they call it bridge priorities, and port priorities, just like LACP. Well, guess what? If you know what the default bridge priority is in spanning tree, you already know what the default system priority is in LACP, 32,768. And just like in spanning tree, where a lower number is a better number, is more priority, same thing here in LACP. The lower the number is, the more preferable it is. So why do we care about this? This really comes into play when, LACP is dynamically negotiating an ether channel. When two systems initially detect each other with LACP packets, they'll see who has the best system priority. Just like spanning tree. By default, they'll both have the same priority, 32,768. That is configurable, by the way. So they'll end up seeing whoever's got the lowest MAC address, just like spanning tree did it. Now, once a system has been identified as the LACP master, basically, that switch is in charge of determining which ports are going to be bundled into the ether channel. Where that can really come into effect is if there's a mismatch of ports. For example, take a look at this diagram right here. In this particular case, on the top switch, we've got, well, actually on both switches, we have 9 ports configured to be in our channel group. Now we know that only 8 of them will actually be active and 1 will be in standby mode, but which one will be in standby mode? Because we have a mismatch here. The switch on the top believes that port number 1 has a port priority of 1. Now remember, the lower the number, the higher the priority. So a priority of 1 is like super, super important, super critical. So this is saying, okay, of my 9 ports, definitely switch number 1 on top, the top switch, believes that his port number 1 should be part of that ether channel. The switch on the bottom thinks that his last port should be part of the ether channel. Now who's going to win? Well, it's going to be the switch that ends up becoming the LACP, has the lowest priority here, that has the best number, which is the switch on the bottom. The switch on the bottom with a system priority of 4,096 is going to be our LACP master, and that's the one that's going to make all the decisions about which ports get bundled. So, which ports will get bundled? Well, remember, think about how spanning tree did it, right? With spanning tree, you had the sending port ID, and that sending port ID was composed of 2 pieces of information. You had the port priority, and you had the port ID. And if all the port priorities were defaulted to the same number, basically the lower the port number, the better the port ID. In other words, a port number of fast Ethernet 0/1 had a lower, better port ID than a port number of 0/2. So in this particular case, if the bottom switch is the winner, which it will be because its system priority is the lowest, he'll say, okay, number 1, I'm definitely putting port number 9 into my ether channel because that's got the lowest port priority of everybody. Now I've got 7 ports left that I could bundle into this ether channel. Which ones will I select from amongst myself? Because I'm the master here. Well, he'll start and he'll say, okay, do I have any other ports on myself that have distinctly different priorities? Nope, they're all the same. They're all 32.768 when I look at the remaining ports. So he'll say, okay, since they're all the same, let me take a look at the port numbers. I'll start with the lowest port and work my way up from there. So what we're going to see in this diagram is that our 8-port ether channel will be consisting of ports 1 through 7 and port 9. So port 9, because the switch on the bottom is the master and he decided that was the best port of everything with a priority of 1. And then of the 7 ports that were left, he chose ports 1 through 7 to add to port 9. And then just some other useful ether channel commands. You can use the command show ether channel load-balance, like in this case here, because we know that the way ether channel works is there's an algorithm in the background that says, okay, when a frame comes in, I'm going to take some bits out of this frame and figure out, based on those bits, which physical cable I use in my ether channel to transmit this frame. As we can see here in this particular output, if we do show ether channel load-balance, this is using the source MAC address. So it's going to take the source MAC address of every incoming Ethernet frame that needs to go across the channel, extract some bits, do like an XOR or something with those bits, and then based on that, select a particular cable. So what that means is that, let's say your laptop is sending thousands of frames through this particular switch. Now those frames could be going anywhere to hundreds of different destinations, INE.com, Google.com, FoxNews.com, whatever. But as they get into that switch, if all those frames need to go through that ether channel to get their destination, guess what? They are all going to go across the exact same cable because they're all coming from you. Your source MAC address is never going to change, and with this default load balancing algorithm, that's what's going to select to decide which cable. Now, if you decide, well, I want a little bit more variation than that, you could change to a different load balancing algorithm. As you can see here, there's well, this doesn't really show you, but there are other options like source IP address, destination IP address, both using source and destination IP address, using source and destination MAC address. You can even use TCP and UDP port numbers as part of the load balancing algorithm on some switches. So you should be aware that there is a little bit of flexibility there from a configuration perspective. Another useful command is the test ether channel load-balance command. So with this command, you could say, all right, I want to be able to predict, forecast which link in my ether channel is going to be used to transmit a particular frame from a particular source. So in this particular case, now that we know our load balancing algorithm is using the source MAC address, I could say test ether channel load-balance interface port-channel and then give it my channel group number that I selected. Then say MAC and then type in like the MAC address of my laptop. And it'll show me that my laptop will always choose physical port 0/5 or 0/9 or something in this ether channel. So that's the way you can see it in advance. So that concludes this review of basic switching technologies. Everything there, almost everything is from the CCNA. A few little scattered nuggets here that were new for the CCNP level. And in our next video, we're going to take this to the next level by talking about something called multi-layer switching. What is it and how does it work? I'll see you in that video.